Hi guys and girls, today I'm going to kind of shift towards a new area of calculus, which is basically also kind of a bridge to real analysis, and it's called functional analysis. So really all there is to it is just looking at second derivatives, which I'll explain in a second, and looking at local maxima, local minima, at the maxima values of a function, minima values of a function, points of inflection, and I'll explain all of them in this video. And then hopefully in the next videos I'll also get to show you some theorems to do with functional analysis. So first kind of concept I want to introduce you to is the idea of a second derivative. So say we have the second derivative of the a second derivative is the same thing as the derivative of a derivative, right? So if we work this out, and f of x, let's take it to be, for example, 6x squared. So then how would we do this? We would essentially get 12x in the first time. When differentiating it, you will get 12. And it's very important because in terms of motion, if you have a function in terms of displacement, its second derivative will be acceleration. So then that's very useful. And you can use acceleration, or in this more generic case, the second derivative of a function, to show where you have a maximum point and where you have a minimum point. So a maximum point is basically a maximum point can belong to two categories. It can be an absolute or global maximum point, or it can be a relative maximum point. So a relative would be something like any place in this function where we can see that the value is significantly, or even not significantly, if it's bigger than its neighbors, its neighbor points. So we see this neighbor point over here is small, has a less. Okay, so this value here seems to be at a peak in this so-called neighborhood. And all it means is just in a neighborhood we just have a point and its corresponding points which are infinitesimally close. So points which are essentially like 0.00001 arbitrary units apart from the right and from the left. And so why we call it relative maximum point is because we can't determine that this is the absolute, the largest value of y in this whole function. But this, for example, along the interval a, b, and I'm gonna make it an open interval, and so an open interval just means that it's like something like that. And so here we see that this is the biggest, the largest value of y, so this is the absolute maximum point. And equally this is the smallest value of y here, so this is the absolute minimum. Then if you have a point which is slightly smaller than its neighbours, and like here, then you could say that this is a relative minimum. That's really basic. But now, if we look at something a bit more interesting, we can kind of have to cover the following prerequisite, which is concavity. Concavity of a function. I think in America they tend to stick to concavity, whereas in the United Kingdom they tend to talk about concavity as opposed to convexity. So I'm just going to present it to UK students, A-level students first. So the way we think of the function's curves, if the second derivative which is, by the way, just like that. It's double prime symbol. If it is bigger than 0, i.e. it's positive, that means that the second of a double rate of change of that function is positive, which means that over time you should get a sort of a sort of convex shape. If you're thinking of say, so the gradient here, the gradient rate of change increases, and that's exactly what this means. Then you should have this sort of curve. So that means if this is the y-axis, then you should get the sort of, in here we can get a quadratic, but it doesn't have to be that extreme. It can be something as minor as rate of change increasing like that slowly. As long as the rate of change, the instantaneous rate of change increases over time, then that we can say that is convex. Whereas if the opposite is the case, so if we end up with that kind of curve, which means that the rate of change decreases over time, then we can call it concave. I think in AP calculus we tend to call this shape here down concave, and this up concave, because in America we tend to think of it as, I don't know, as a lens perhaps. So like if you have this kind of curve, and this is the positive x-axis, this is the positive y-axis, then you can think of it as, there's like an integral here, and it's like the shape of something, and that shape will be concave, just like here. It would be down concave, because if you're looking at the integral in the negative axis, it would still be concave. So yeah, I think that's the basic kind of stuff you need to know. Oh, and something that's very important is point of inflection. Now, point of inflection, you can see it here. I can see it here as well. Possibly here as well, but I'm going to stick to those. That's when the concavity or the convexity of a function changes. So you see here, the rate of change is kind of decreasing. So you see that the slope here is something very kind of moderate. Here it's clearly very negative, so it's decreasing. And so what we'd expect if it wasn't a point of inflection is you'd expect the rate of change to kind of decrease steadily, like almost like that. And that's kind of where you get an asymptote. But no, but it changes direction. It becomes more positive. And here it straightens up, and here you see that the gradient is equal to 0. So it clearly increased. So if here if the gradient here in x minus h, where h is like a really small point, is not the same sign. I'm gonna put it this way: if the sign of, just like that, is not the same as the sign of fx plus h, where h is like infinitesimally small, and x is that actually c. Let's call it c. C is that point of inflection. Then you can see that c is clearly a point of inflection. But really, any minor increase in a function can matter. So what we're talking about here is the rate of change, the second derivative of that function seems to be increasing until we reach that point, and then seems to be decreasing after that point, or vice versa. And that just means that you won't end up with that asymptote, but the function we had in a different curvature, if you like. And that kind of relates to curvature in multivariable calculus as well. And I'm hoping to make a series about multivariable calculus as well, but for now, those are the basic kind of ideas, and I'll probably discuss the mean value theorem and possibly some other things. Maybe I don't know. There'll be tons of topics to talk about, but see you in the next video. I hope this wasn't too convoluted, but really the stuff here is not too advanced, and all those points where the gradient seems to be equal to 0, that's called the stationary point. But just note that. Okay, see you in the next video.